Hey everybody, in our last video we looked at using methods of inference to test claims using proportions. Today we're actually going to talk about, continuing the idea of inference, we're going to talk about two-tailed tests. Now, as part of this, we're going to talk about how these differ from the tests you did last week, and also why these differences exist and why we have these two types of tests. A lot of what you're going to see today should feel very similar to what we did last week, so what I'm really going to focus on more are the differences and why those differences exist. So let's start with an example from the previous video. So you should recognize this example. This is our peach wave example. So the most popular flavor of frozen yogurt sold is strawberry. There was a claim that 44% of all customers have strawberry as their favorite flavor. You suspect that strawberry is not that popular in Brookfield, so you sample 60 randomly selected Brookfield Peach Wave customers and find that 21 said that strawberry is their favorite flavor. Do you have significant evidence at the alpha equals 0.05 level that the true proportion of Brookfielders who prefer strawberry is less than 44%. So we also talked last week about biases and how they can influence our thinking. I want to highlight a couple parts of this problem that are typical with this type of phrasing, and I just want to bring our attention to them in the context of some of the other things we talked about last week. Notice that I use the language, you suspect that strawberry is not that popular in Brookfield. That immediately indicates that that was a sort of a subjective feeling that you had, and any time that occurs, there's a possibility that there could be reasons for that other than, what's actually happening in reality. Also notice that the entire structure of the test was based on the idea that we think that the true proportion of Brookfielders who prefer strawberry is less than 44%. So right from the beginning, we had a belief about what was actually going on. We weren't approaching it from truly neutral ground. So the question in a case like this is, could someone argue that this whole process was actually biased? We came at it from the idea that we already thought that strawberry was not as popular in Brookfield as Peach Wave said it is all over, the country. Now, you might look at that and go, well, is it really that significant? We did find that the proportion 21 out of 60 was less than 44%. If you recall from our actual study, the p-value was actually greater than 0.05, so we didn't end up rejecting the null hypothesis. But we do see that the percentage we got was less than 44%. But still, this can be a problem for some people. So let's talk about the problem with one-directional tests. Doing a test like this is called using a directional hypothesis. Our alternative hypothesis used greater than or less than. So in that case, our alternative hypothesis was p is less than 0.44. Another name for this type of test that I did not use last week because we weren't contrasting it with what we'll talk about this week is a one-tailed test. And the question that statisticians face all the time is doing a one-directional test always ethical? Let me give you an example of where something like that might come up. So suppose we want to test a disease treatment and compare the recovery rate of patients who receive it to those who received a controlled treatment. When we do a test like that, we might assume, if anything, that we would think more patients would recover with our treatment as opposed to the control. However, is it possible that the results of the test might actually go the other way? Could fewer patients recover with our experimental treatment? And if you think about it, of course that is possible. Now, why might that happen? So perhaps the experimental treatment actually has negative side effects that are actually worse than the disease that they're treated, or the experimental treatment can make the symptoms of the disease actually worse. So there's lots of ways this could go. So the idea here is that even though we would want to assume that our results would go in one direction, they may actually not when we do the test. So how do we get around this problem of one-directional tests? Well, don't go in one direction, go in both directions. So the idea here is that instead our alternative hypothesis would be what we call non-directional. Instead of testing less than or greater than, we will test not equal to. Another name for this type of test is the two-tailed test, as opposed to a one-tailed test. And now we're going to talk a little bit about how does it work, and we're going to do so in the context of the peach wave example that we saw before. So in our peach wave example, the number of people we surveyed was 60, and our p-hat came out to 0.35, which is the 21 divided by 60. Our sampling distribution mean was 0.44, and our sampling distribution standard deviation was 0.0641. I'm not going to redo those calculations. They were in the previous week's video, so you should have those. So what this actually looks like as a sampling distribution is here we see the familiar normal curve. The mean is exactly at 0.44 on the x-axis. That's what we know here. And this curve is drawn with the standard deviation of 0.0641. I have marked with a vertical line where our p-hat of 0.35 falls on that. So it was below the mean. And from there, we used normal CDF to find the area under this curve from negative infinity to our p-hat 0.35. And that gave us the p-value, the area of the tail, which was about 0.0802. So that's where the one tail comes from. We're finding the area of one tail of the normal distribution here. So we could have done this test as a non-directional test if we wanted to. A couple things would change, but a lot of things would also stay the same. What would change is our alternative hypothesis. Instead of being p is less than 0.44, we would change it to p is not equal to 0.44. This allows us to be non-directional. We're assuming it might be greater than or less than. But our p-value will also change. It will combine the area that we found before, that tail from negative infinity to 0.35, with the exact same area on the other side of the sampling distribution. This is the second tail, and it's basically saying it's allowing the extreme of the statistic to go in the second direction also. So what I want you to think about is what would happen to the p-value if we added this same tail just on the other side? You should have realized that adding the second tail will literally double the p-value because the opposite tail will have the same area. So it will go from 0.0802 to 0.1604. Another conclusion of this is that non-directional tests will always have a higher p-value than a directional test done the same way with the same sampling distribution and p-hat. So what's important here, will this make us more or less likely to reject the null hypothesis in a two-tailed test? So think about that before moving forward. So a higher p-value will make it less likely for our p to be below alpha. That will mean in turn that we will be less likely to reject the null hypothesis. So we're going to be less likely to say we have significant evidence of a difference in our values. This gives us a more conservative test. We are less likely to get a false positive test. So because we're less likely to get a false positive, and like we said before, because non-directional tests feel less biased, they feel less like we're assuming the results will go in a certain direction. In professional practice, two-tailed tests are generally perceived as better than one-tailed tests. I put better in quotation marks only because that's really a subjective interpretation of these points. But when you read professional statistical papers, very few actually use one-tailed tests. They usually use two-tailed for these reasons. An appearance of less bias in the construction of the test and the lower likelihood of rejecting the null hypothesis and getting a false positive. Because you have to have a lower p-value before you double it in order to make sure it's going to be less than your alpha. Now, What you're going to have to decide as you do these problems is whether or not you're going to do a test as one directional or two. But in the problems we give you, you're going to let the language of the problem be your guide. You should probably do a one-tailed test if in the language you're asked to test whether something is greater than or less than. If we specifically use that term, we're implying a direction, and so you can use a one-tailed test. When you do a one-tailed test, you will use the direction of the test to know if your p-hat is your upper or lower bound of your CEF. If you're testing greater than, it will be your lower bound. If you're testing less than, p-hat will be your upper bound. You should use a two-tailed test if the language says not equal to or different from. If the language never implies a greater or less than situation, you should run a two-tailed test. And in that case, you're going to use your p-hat's location relative to the mean to know if p-hat is the upper or lower bound of your normal CDF. So because we're not going to give you a direction, you're going to have to infer how to do your normal CDF to do it correctly. So we're going to see an example of that to hopefully make that clearer. So let's take a look at an example. So suppose that it is known that in the general population, 11% of all people are left-handed. And you do a random sample of 1,000 Brookfielders and find that 92 of them are left-handed. So the question is there significant evidence that the true proportion of left-handed Brookfielders is different from the general population proportion of 11%? Use an alpha level of 0.05. So you might have noticed that I used the language different from. I'm not saying greater than or less than. As soon as you read that, you should immediately know that this is going to be a two-tailed non-directional test. So let's actually do the computations we need to do the test. And again, most of them are the same. We have our null hypothesis, which is p is 0.11, the 11% we were given. Our alternative hypothesis now is that p is not equal to 0.11. So there's no direction implied. Our p-hat is 92 out of 1,000, since we surveyed 1,000 people and 92 were left-handed, and that comes out to 0.092. Now, one thing we need to note is that 0.092 is below our sampling distribution mean of 0.11. So it will end up being the upper bound when we do normal CDF, because that first tail is going to be the tail below the mean, not above the mean. So that's important to note. If p-hat were greater than the mean, it would end up being the lower bound, and E99 would be the upper bound, positive infinity. So our sampling distribution mean, just like before, is the null hypothesis value of 0.11. Our standard deviation is going to be found the way we have been finding it. Let's bring up our calculator and actually do it. So we have square root of 0.11 times, I know that 1 minus 0.11 is 0.89, and I'm going to divide that by 1,000. And this gives me a value of 0.00989. I'm going to say that's about 0.0099. And now we have to do our normal CDF. So again, our p-hat is below our mean, so it's going to be a left tail. So p-hat will be the upper bound, and negative infinity will be the lower bound. So now I have to actually do our normal CDF. So let's go into our distribution menu like we always do. Normal CDF. Our lower bound is negative E99. Conveniently, it's already in there. 0.092 is our upper bound. Our mean is 0.11. And our standard deviation is 0.0099. This will give us the area of that left tail, which is 0.0345. However, this is a two-directional test, or a two-tailed test. So our p-value has to also include the tail on the opposite side, which will have the same area. So the p-value will end up getting doubled. So the p-value of our test is actually 0.0690. Now we can compare it to our alpha. And we should see it, they wanted us to use 0.05, and 0.0690 is greater than 0.05, so we must fail to reject the null hypothesis. We do not have significant evidence at the alpha equals 0.05 level that the true proportion of Brookfielders who are left-handed is different from 11%. So notice instead of greater or less than, I use the language of the problem and I say different from. That indicates again that we used a non-directional test, a two-tailed test. So the one thing I want you to note here, because it's really important, is that the area of the original tail was 0.0345. If we treated this as a directional test and only used one tail to do the p-value, that would have come out as less than 0.05, and we would have rejected the null hypothesis. So here's an example where, because it was a two-tailed test, we ended up failing to reject. This goes back to the fact that in a two-tailed test, you get higher p-values, so you are less likely to reject the null hypothesis. You're more likely to fail to reject. And that, again, lowers the probability of a false positive. So I wanted to illustrate that through this example because it's an important quality of two-tailed tests that they get higher p-values. So I hope that this has made sense for you, and going forward you're going to see examples of both one-tailed and two-tailed tests, and you're going to use the language of problems to help you choose between the tests.